7.1, graphing exponential equations. This is the last section of your pre-chapter 8 stuff. Go us. Moving on, next slide. An exponential function, it is a function where the base is a constant, which means it's a number, and the variable is up in your exponent. This is the one on the day where we did that intro worksheet that I was like, you have to go to your book and look at this picture, otherwise it ain't going to make sense as to why it's set up. This is why, right here, okay? Because your base of an exponential, it can be any number, basically. All right, any number bigger than 1 will make it a graph. It can be 1, 2, 3, 4, 5, what have you. Okay, so it can be any number that you want it to be, or that it ends up being. Okay, now, an important definition, especially for next chapter, is right here. It's called an asymptote. Yeah, get them out now. All right, they're asymptotes. Very good. An asymptote is a line that the graph approaches but never crosses. Okay? It is a line, it's an imaginary line where a graph approaches it, but it never crosses it. Once you start getting into the upper level of functions, and for this class it's basically exponentials, reciprocals, and rational functions, those three. We're doing one now, we'll do two next chapter. Once you get into those three, you got to start talking asymptotes because you get into some funny looking shapes. Exhibit A, B and C will be later. Okay? So these graphs are going to basically be curves where they'll almost touch and keep going up, but never cross some line. Okay? Or they'll keep going this way, this way, this way, and they'll never cross some line. You're going to have to start figuring out what those lines are. That's called asymptotes. Okay, they're imaginary lines that the graphs do not cross. We're going to have two types today. One is going to be the parent function of growth. From left to right, you're increasing. That's why it's called growth functions. The other one is decay. It's because from left to right, you're decreasing. Once again, very creative on the names. Any questions on this? Everybody good? Great. Moving on. Graph y equals 3x. 3 to the x. You're going to take your calculator, put in the function y equals 3 to the x. You're going to hit table. And after you hit table, for these nice parent functions, you do have some nice ones. Okay, you got coordinates of 0, 1, 1, 3, and 2, 9. And then you go over and graph them. So 0, 1, 1, 3, and 2, 9. Write that. Okay, if you go the other way, you'll see like 1/3 or -1 goes with 1/3. -2. The decimal numbers are ugly, but it goes with 1/9. -3 goes with 1/27. -4 goes with 1/81. And they keep on keeping on getting what? They keep getting smaller. Okay? They keep getting smaller, but they are never what? It's never 0. Never 0. Okay? Think about the biggest negative number you can. -100. Take it to the third power to that, it's still not 0. It's something insanely small, but still not 0. Okay? So that's why when you draw this graph, you have to make sure that you don't cross the x-axis. Okay? Make sure that you don't cross the x-axis whenever you are drawing exponential graphs, or whatever the asymptote ends up being. Now, as far as accuracy with this graph goes, I'll look at the points where they should be there. Those whole numbers. After that, it's just a curve. That's it. Okay. So don't worry super much about accuracy here. Basically, make sure you don't cross your asymptotes, and those points are somewhat close to correct. All right. And like I said, you can if you look real close, you can kind of see me increase again. Like I said, I'm not worried about that a little bit. Okay, Mitchell.
Wait, so you said you don't draw the line on the x-axis?
Correct.
No, just right above.
Just right above it. Okay. Not if you get on it, I'll be okay. All right, because you are getting insanely small. Don't cross that line though. Okay. Don't cross that line.
And do we have to like the -1 and the 1/3 and the 1/9?
No, I just did that for show. Okay. All right. The two things you do have to put though. On the pen. There you are. And even though it doesn't say it, I want you guys to get in this habit. Domain and range. Okay. What's your domain on this guy? All reals. Okay, and what's the range?
All reals.
Y's that are bigger than or equal to 0. And technically just bigger than. Right, because you never hit 0. Alright. Okay, this is the good old, transformation slide. Tells you how it moves and things. Most of it's true. Most of it's, like I said, most of it's staying true. The K on the outside does your vertical shifting up and down. The A in the front does your stretching, compressing. The weird part is the H is up in the exponent now, because remember these are exponential functions. And that's where the variable is going to be. So that's where the function itself is in the exponent, just like if it was in the radical or in the binomial being squared for a quadratic. Okay, so that's a little bit of an odd part that you have the exponent up. So your exponent could say, x minus 2. All right, as a quantity. So you have to be careful when you graph that. But pretty much that slide is pretty much the same stuff it's been all sections. So everybody good? Great, moving on. So graphing, y equals 2x plus 1, or 2 to the x. You put it in, you get a table. That was a beautiful y. Let's try again. Hey, there it is. Alright, so this time it's 0, 2, 1, 3, 2, 5. And then you go plot those points. 0, 2. Change color. There we go. 0, 2, 1, 3, 2, 5. And then it would kind of shoot up in that manner, right? Alright, now if you look at your table, and always do look at the table, because that'll tell you basically what your asymptote across the bottom is. Alright, because if you keep going down, 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 you eventually get so small once you hit negative 15 that it can't show the decimals numbers anymore, so it just shows you what? 1. Alright, so now that's the number, that's the line that's your asymptote, not the 0, but 1. So it'll switch from problem to problem, or function to function. So you have to make sure that you pay attention to where it's at, okay? And that's definitely because of this plus 1 right here, right? It shifts the graph up 1. Okay, so it shifts everything about it. The graph itself, and the asymptotes too. Domain, all reals, and your range, or y is greater than 1. Not equal to, remember. You'll never touch that line. Okay. Even though your table shows you negative 17, 1, think about it. You're getting smaller and smaller and smaller. It's not because it's not exactly 1. It's because you keep getting too small that it won't show you. Okay, so the ranges here are strictly greater thans. Okay, does that make sense?
Mm-hmm.
because you're never touching 1.
So anything exponent is never going to have equal to?
Right. Everybody good? Alright, so for negative 1/2 times 5 to the x minus 2 power. I'm going to show you how to do this, alright, in case you didn't. Y equals, clear that mess. Okay. So, what I do parentheses. Always parentheses are not my best friend, but close to it. Negative 1/2. And the reason I do that is because my 5 is what's taken to a power. So times 5 to the x minus 2 power. If you have a box like mine did, and like most of you guys do, you can just put x minus 2. If your caret pops up, you need to put that x minus 2 in parentheses. So group it as the exponent. Okay, everybody good? Okay, we're going to hit graph. And then we're going to obviously, hopefully, zoom to the right spot where we're supposed to be as soon as it's done graphing. There we go, zoom 6. And there you go. Okay. Alright, that's what you should somewhat look like. Alright.
Is your line going on the...
And yeah, that's the only thing, okay, since obviously it's black and white, so it's a little hard to see, but it keeps going up and up against that x-axis. Okay, but you just can't see it. Alright. Let's go to the table, check it out. Let's go the other way though. Because see, 1's at negative 0.1, 0 is at negative 0.02, 1's at negative 0.04, and then see how you get smaller? Alright. See how it keeps getting smaller and smaller and smaller and smaller. Alright, so you are touching that x-axis. Okay? Now, the only real bad part about this one here is that you really can't take it to get a nice solid picture. Okay? It's kind of bad for that. So what you should do is pretty much just kind of do your best, you know. Yep, something like that. Okay, looking for some accuracy here, but not a lot. Okay. All right, just so you can see what it does differently when your base is not a whole number. So 1/3 x, not 11/3. Hold on. So when your base isn't a whole number, it's a fraction. That's when, and especially a fraction between 0 and 1. That's whenever you switch and change up in what you put in, as far as the direction it goes from growth to decay. Okay, so this one's got points. Let me write them up over here. Of -2, 9, -1, 3, and 0, 1. Okay, so then like that. Except it goes the other way, right? So it's decreasing. It's decreasing from left to right. But that's because of your base. Okay, your base being 1/3. Alright. But everything else about it stays the same. Your domain is still all reals. The range, you know, it's still y's greater than 0 on that guy.
On the
So
last
it just
one,
flips.
was it y is less than 0?
Yeah. Yep. Okay, now the word problems to this are pretty simple. To be honest, this is the freshmen did this for me last chapter for them. They did a pretty good job at it. Words are you can model exponential growth with a constant percent increase or decrease over specific time periods using the following functions. A of t equals a parenthesis 1 plus r to the t power, or a of t equals a times the parenthesis 1 minus r to the t power. the functions can be used to find, yes, typo, I know, the amount a of t after t number of time periods, where a is the initial amount and r is the percent of increase or decrease per time period. So that means, all that means is that time can change from problem to problem. You're just talking about whatever context of time the function is talking about. Okay, for example, if it said it's a function of minutes, then everything in time-wise would have to be in minutes. If it was a function of months, everything in timeline would have to be in months. Make sense?
Yeah.
Okay. The expression r1 plus r is called the growth factor. The expression 1 minus r is called the decay factor. Obviously, you're going to use the plus for growth, the minus for decay. Alrighty? Questions on this so far? Those are your formulas. Because here we go. Let's write a program. New. I don't need to write it. Hold on. Wrong button.
Is this gonna be on video though?
Uh-huh. I'm live right now.
So she'll be able to hear my voice later?
I don't know if it picks up that well. She'll be able to hear mine though.
Hey, Meows.
Because I'm the one that matters, to be honest. Okay. I'm going to name this guy E. If it would click. There we go. E, X. Where's my P? N-O-P. G. T. H. Exponential growth. See that?
It says X.
Very good, Mitchell. I'm so glad you can read. Alright, or name it whatever you want it to name, okay? Enter. It's a pretty simple program. We need 3 prompts. We got one formula. We're going to display that answer. So to get your prompt command, you hit program. Go to the right. It's number 2. So we're going to prompt an A. Everybody good? Prompt A. Hit enter. We're going to prompt an R. Hit enter. And we're going to prompt a T. Hit enter, and I like to be cute and leave an extra space. Okay. Put in the formula, which is A, parenthesis, 1 plus R, close up parenthesis, to the T power. And then remember, we need to store that somewhere, so I'm going to store it in X.
Did you press the X button?
I pressed stow first.
But then did you press like?
Yeah, X up top. Yep, X. Either one works. Okay. There's your stow button, which brings up that arrow from right there.
Is that squared to T?
Huh?
Is that squared to T?
Caret T.
Yeah.
Exponent. Okay.
Wait, what did you do?
Nope.
And then what's the arrow? How do you?
All right. I hit enter twice. Program. Right. Display 3. This is number 3. Display. X. Enter. Second. Quit. And it's right. Oh, sorry. A little fast. Oh, my bad. a lot fast. All right. Ready? Wherever you're at, pick up. Okay. Program. To the right. Let me get there. Hold on. Nope. Wrong one.
Display and then you put X.
Program. Yeah, program. Display is number 3. You hit enter. Make sure you hit right once you hit program. Right. It's in the input output. Second menu. Okay. Display is number 3. And then hit X. When you hit enter, which I'm going to hit clear to go back, you hit X after that.
And then you hit enter after X.
Yep.
Enter and then you're done. Then you put second quit.
And then second quit.
Alright.
Okay. Now, there are a couple of variations you can do with this. Number 1, you can obviously, go and write a second program for decay. We're not going to take that time, but it won't take you long if you just follow the exact same prompts. You just make it a minus and not a plus. Okay? Some of you probably already did it. All right? The other thing you could do is just kind of write one as exponentials and then put your growth in there, put a pause in there, and then put your decay in there. Okay?
So like a mini.
Kind of like how the quadratic formula program, when we did that one, if you edit these programs, you can go and look at the code. Okay? And if you look at the quadratic formula code, oops, wrong button. Okay, here it is. When we did the discriminant, when I did it, I sent it to F. Everybody see that? Okay? After you sent it to F, I hit display discriminant, and it displayed to F, right? Discriminant shows first. And then I hit a pause, right? Because then what's it going to show us next? The solutions. Okay, so you do the discriminant. I put display discriminant because we were cute back then. Put display F and hit pause, so that way it wouldn't just spit it out rapid fire. Okay, so what you could do if you wanted to get a little more advanced with this, take your exponential growth one, the one we just wrote, instead of finishing it, put a pause, and then after it, put the decay. And then whenever you're working one problem, you ignore whichever one you don't want. It means it's one program for two sets. Make sense?
Would you go through and type it again?
You would.
A minus or 1 minus.
You would just all you would have to do is put that pause in, and then put in the formula
Okay.
for decay, store it to a different variable, display that variable, done.
Okay.
Make sense?
Yeah.
Okay. It's like I said, it's your choice whether you want to write a new one, or tag it onto the second one. Okay. Once again, as with all programming in here, if you do it, make sure you show me the setups, which is what we're going to talk about right now. Okay. So. Okay, the first U.S. Census, I'm not going to blow this all the way up. The first U.S. Census, there we go, was conducted in 1790. At the time, the population was 3,929,214. Since then, the U.S. population has grown by an approximate 2.03% annually.
Nice.
Estimate the population in 1890. Okay, so to do this, you had to do two things. Number one, you had to make sure you have your function correct. Okay, so we're going to do that. So y equals a. Are we losing people or gaining people?
Gaining.
Gaining, so we're going to have 1 plus our rate to the t power. Our initial was 3,929,214. 1 plus, or not a space. Your rate is 2.03%, so what number are you going to use? 0.0203. And then how many years is 1890 after 1790? 100. Okay, everybody got that? Because I want to delete it.
Oh, okay.
All right.
Discard.
That's a big number.
Okay, so hopefully, let's make sure this is live lesson teaching. So hopefully this works. Enter A 3,929,214. Right?
Yes.
Great. Enter rate 0.0203. Enter T 100. Enter the growth.
That's what I got. Heck yeah. Yep.
I want to try.
Okay.
9, 2, 9. I did this.
You like it?
No, you round down. I don't want 0.98 of a person. Nor do I want you to tell me there's a whole person there when there's only a half person. So round down.
This person just doesn't exist.
Okay. That 0.34 of a person doesn't exist.
Well, yeah.
Sorry.
Do you not want to use your imagination?
Nope. I want my people to have all their. I want their all to be there. Okay. Now.
What if you only have like a couple legs?
Now, since you're doing growth, You hit enter again, it's going to spit out this decay as if it were a decay problem. But you don't care about that number because we're not doing a decay problem. We're doing a growth one because our population was increasing. Okay, make sense? Okay, last one. A cup of green tea, contains approximately 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. Write a function that would represent the amount of caffeine remaining after drinking a cup of green tea. Then estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of green tea.
So is that decay?
It is decay because you're disposing of the green tea, your milligrams of caffeine, right?
But you can have definite.
Okay.
Right?
Yeah, oh, definitely. All right, so y equals, well, beautiful y's. My y's are on point today. 35, I'm just going to go with it. It's 2:55 on a Friday afternoon. You guys can make do. 1 minus 0.125, 3. Make sure, real quick, make sure you show me the setup, okay? Because if you show me the setup and then you put something in your program wrong, I will be lenient. You don't show me the setup, you put something in your program wrong, and then you mess it up, I will not have mercy on your soul. Rachel.
Does it matter if you put a 3 or 180 hours, minutes? Would you change it?
Yeah, it would. You got to do. Your context in hours, so you got to put hours.
So whatever the problem is.
Right. Whatever it says, that's what you got to put. Okay. It'll throw your scale off. Alrighty.
I love when I have the perfect amount of programs that my quadratic program is the fourth one because quad is 4. How long is it?
Okay, so you put this one in. You get 49.833 first, but we don't care about that one because that's if it was adding the milligrams back in at that rate. We don't care. Mitchell, you should get 23.447265, whatever.
6.
Okay?
How
Alrighty.
many places do you round to?
2, 3, 7.
You should do 2 because then it's 4 and 5 and then it's
I like 4.
Doesn't matter to me too much. Okay? Everybody good?